Pick up an ice cube. It floats. Of course it floats. You've known this your whole life. Water freezes, becomes ice, floats. Obvious. Except it isn't obvious. It's one of the strangest things matter does. Take almost any other substance you can name, melt it, then let it cool. The solid that forms is denser than the liquid. Iron sinks in molten iron. Wax sinks in liquid wax. Freeze virtually any liquid and the solid goes to the bottom. That's the rule. Molecules slow down, lose energy, pack more tightly, take up less space. Solid, denser than liquid, sinks. Water does the opposite. Ice is less dense than liquid water, about 9% less dense. And that number, that single anomaly in the behavior of one molecule, has consequences that reach from the geometry of electron orbitals all the way to the history of life on Earth. Most people have been told the explanation: hydrogen bonds. Fine, but what are hydrogen bonds? Why does water have them? Why do they make ice less dense? And why does it matter? Those are the questions. Let's follow them. First, let's be precise about how strange the density inversion actually is. In most substances, freezing means the molecules lock into a crystal lattice, a regular, repeating arrangement. And that lattice packs them more tightly than the disordered liquid phase. The molecules are closer together in the solid, more mass per unit volume, higher density, solid sinks. Water does something different as it cools. Liquid water actually reaches its maximum density at 4 degrees Celsius, not at the freezing point, but 4 degrees above it. As you cool water from room temperature down to 4 degrees Celsius, it gets denser, normal enough. But then, as you cool it further, from 4 degrees Celsius down to 0 degrees Celsius, it gets less dense again. And when it freezes at 0 degrees Celsius, ice has a density of 0.917 grams per cubic centimeter, compared to 1.000 for liquid water at 4 degrees Celsius. That 9% density difference is enormous in practical terms. When water freezes in a pipe, it expands by 9% and the pipe bursts. When water freezes in a crack in a rock, it expands and splits the rock. Frost weathering, one of the primary forces shaping landscapes over geological time. When a lake surface freezes, the ice is lighter than the water below it and stays on top. This is so unusual that it defines a whole category of anomalous behavior. And understanding why it happens requires going all the way down to the molecule. A water molecule is 2 hydrogen atoms bonded to 1 oxygen atom. Simple enough formula. But the geometry matters more than the formula. The bond angle, the angle between the 2 hydrogen atoms as seen from the oxygen, is approximately 104.5 degrees. Not 180, which would make the molecule linear. Not 120, which would be a flat trigonal arrangement, 104.5 degrees. This specific angle comes from quantum mechanics, from the way electron orbitals organize around the oxygen atom when it bonds to 2 hydrogens and retains 2 lone pairs of electrons. Now, oxygen is what chemists call electronegative. It pulls electron density toward itself more strongly than hydrogen does. The result of this unequal sharing is that the oxygen end of the molecule carries a partial negative charge. The electrons are more likely to be found there. And the hydrogen ends carry partial positive charges. The molecule is electrically asymmetric, polar. And polarity means attraction. The positive hydrogen end of one water molecule is attracted to the negative oxygen end of a neighboring water molecule. This electrostatic attraction is a hydrogen bond. Hydrogen bonds are not covalent bonds. They are not sharing electrons between atoms. They are attractive forces between partial charges, about 20 times weaker than a covalent bond. On their own, they're modest. But water molecules can form up to 4 hydrogen bonds simultaneously. Each oxygen has 2 lone electron pairs that can accept hydrogen bonds from neighboring molecules. And each molecule has 2 hydrogens that can donate hydrogen bonds to neighboring oxygens. 4 bonding opportunities per molecule. And in liquid water, most of those opportunities are in use at any given moment. The result is a network, not a chain, not a pair, a 3-dimensional web of molecules connected by hydrogen bonds in every direction. This network is what makes water unusual, almost uniquely unusual. In liquid water, the hydrogen bond network is dynamic. The bonds form and break on timescales of picoseconds, trillionths of a second. At any given moment, a water molecule might be bonded to 3 neighbors or 4, and a moment later the network has rearranged. Liquid water is in constant, rapid structural flux. But it's not random. The molecules are attracted to specific orientations. They prefer to align with partial charges facing each other, and this creates local, transient order even in the liquid state. Liquid water has more structure than a simple liquid like liquid nitrogen or liquid argon. It's structured disorder, a constantly renegotiating geometry. As you cool liquid water, the thermal motion slows. The molecules spend more time in favorable orientations. The hydrogen bond network becomes more persistent, more stable. At 4 degrees Celsius, the molecules are pecking about as efficiently as they can while still moving freely. This is the density maximum. As close together as liquid water molecules typically get. Then, as you cool below 4 degrees Celsius, something changes. The network starts transitioning toward a preferred, stable geometry. And that geometry is different from the disordered liquid. It's more ordered. And, crucially, it's more open. In ice, water molecules arrange into a hexagonal crystal lattice. Each molecule is hydrogen bonded to exactly 4 neighbors in a tetrahedral arrangement. 1 neighbor above, 1 below, and 2 to the sides, roughly. This 4-coordinated tetrahedral network repeats throughout the crystal with beautiful regularity. And here's the key. The tetrahedral arrangement is spacious. When you lock molecules into this specific geometry, the geometry that the 104.5 degree bond angle and the 4 bonding sites naturally prefer, the molecules end up farther apart than they are in the disordered liquid. The crystal has channels and open spaces running through it. It looks like a honeycomb at the molecular scale, hexagonal rings of water molecules with gaps in the middle. The liquid is more disordered, but molecules can slip into those gaps and pack more closely. On average, liquid water molecules are slightly closer together than ice molecules. Higher density. This is counterintuitive. Crystals are usually more ordered and more dense than liquids. Ice is more ordered but less dense because the order it adopts is an open order. The hydrogen bond geometry forces it. You can see this structural signature at the macroscopic scale. Snowflakes are hexagonal, not circular, not random shapes, hexagonal with 6-fold symmetry. That symmetry is the hexagonal ice lattice, magnified by the growth of ice crystals along preferred crystallographic directions. When you look at a snowflake's 6-pointed structure, you are seeing the geometry of the hydrogen bond network reflected up 10 billion times in scale. The molecular architecture made visible. Now let's talk about what this density anomaly actually means for life on Earth, because this is where the physics becomes planetary. If ice were denser than water, if water behaved like essentially every other substance, lakes and oceans would freeze from the bottom up. Here's what would happen. Air temperatures drop below freezing. The surface water cools, freezes, becomes more dense, sinks, exposes more liquid water to the cold air. That freezes, sinks, more liquid exposed, repeat. An entire body of water freezing progressively from the bottom to the top. In a cold enough winter, in a cold enough climate, the whole lake becomes solid ice, top to bottom. In summer, the top layer might melt, but the deep water, insulated by the ice above, never receiving sunlight, might not. Over many winters, many lakes, many ice ages, most freshwater bodies at temperate and high latitudes would become permanent ice or near permanent ice at depth. Aquatic life as we know it, fish, invertebrates, the microorganisms that form the base of freshwater food chains, would be absent from most of the planet. The thermal refuges that allowed life to persist through cold periods would not exist. Instead, ice floats. A layer of ice forms at the surface, and ice has low thermal conductivity, about 2 watts per meter per Kelvin, compared to the 0.6 of liquid water. The ice layer acts as an insulating blanket. It slows the heat loss from the water below. The lake beneath stays liquid. The temperature at the bottom of a frozen lake in winter is close to 4 degrees centiseconds, the temperature of maximum density, where water sinks and insulates further. Life continues. This has been happening through every ice age, every cold cycle, for hundreds of millions of years. The 104.5 degree bond angle of the water molecule created the conditions under which aquatic life could persist through planetary cold periods. A piece of molecular geometry, a consequence of quantum mechanical electron orbital shape, is part of why life is here to ask questions about it. Now I want to address something you've probably heard that is half true and instructively wrong. The classic claim, ice skating works because the pressure of the blade melts the ice, creating a thin water layer that lubricates the motion. The thermodynamics is real. The Clausius-Clapeyron relation, which describes how phase transitions shift with pressure, predicts that increasing pressure on ice lowers its melting point. This is connected to the density anomaly. Because ice is less dense than water, increasing pressure favors the denser phase, which is liquid. Pressure can shift the ice-water balance toward liquid. This is correct physics. But look at the numbers. To lower ice's melting point by 1 degree Celsius, you need approximately 130 atmospheres of pressure. An ice skate blade exerts roughly 1 to 2 atmospheres of pressure on the ice surface, maybe slightly more for a very thin blade. This lowers the melting point by less than 0.02 degrees Celsius. At skating temperatures of -5 or -10 degrees Celsius, pressure melting produces essentially no liquid water. None. The real lubrication of ice skating, confirmed by careful experiments, comes from a quasi-liquid layer. The surface molecules of ice are not fully bonded to neighbors on all sides, unlike interior molecules. Their bonding is incomplete, their motion less constrained. Even at temperatures well below freezing, the outermost layer of ice molecules has liquid-like properties, a mobile, disordered surface on an otherwise crystalline bulk. This surface pre-melting is a quantum mechanical surface phenomenon, a consequence of the incomplete bonding at interfaces. Ice is slippery because of quantum surface physics, not because of pressure. The pressure explanation has been in textbooks for more than a century. It illustrates something important. A mechanism can be real, point in the right direction, and still be quantitatively wrong by orders of magnitude. Identifying the right physical effect is only the first step. Checking whether the magnitude is large enough to explain what you're trying to explain, that's the actual work. Now let me tell you something that should recalibrate how you think about understanding anything. Water is the most studied substance in the history of chemistry. More papers have been published about water than about any other molecule. Its properties have been measured with extraordinary precision. Its behavior has been modeled by quantum calculations, classical simulations, and everything in between. Water has more than 70 known anomalous properties compared to simple liquids. Not one or two, 70. Its heat capacity is anomalously high, which is why oceans moderate climate. Its surface tension is anomalously high, which is why small insects can walk on it. Its viscosity behavior with temperature is unusual. Its isotope effects, the behavior of heavy water with deuterium instead of hydrogen, are pronounced in ways that affect biological systems. The molecular dynamics of liquid water, the precise structure of the hydrogen bond network at any given moment, how it fluctuates, how it responds to dissolved ions and organic molecules, how it behaves at the surface of proteins, is still being actively researched. Ultrafast laser spectroscopy has revealed structural dynamics in water that weren't accessible before. High-resolution simulations continue to refine the picture. And in 2020, experimental evidence emerged supporting something theorists had proposed for decades. At very low temperatures, water may exist in two distinct liquid phases, a low-density liquid and a high-density liquid, separated by liquid-liquid phase transition. Two different ways for liquid water to organize its hydrogen bond network, with a phase boundary between them. The experimental confirmation is recent. The debate in the research community is ongoing. The most common molecule on Earth's surface, the molecule you're mostly made of. The molecule without which no life is known to exist anywhere, and still, in important ways, not fully understood. So, why does ice float? Ice floats because the hydrogen bond network of water adopts an open hexagonal lattice when it freezes, a crystal structure that is more spacious than the disordered liquid. That open structure exists because of the 104.5-degree bond angle of the water molecule and the four coordinated hydrogen bonding geometry it produces. That geometry exists because of the way quantum mechanics distributes electron density around an oxygen atom bonded to two hydrogens. The floating of ice is a quantum mechanical consequence, traced through molecular geometry, through hydrogen bond network structure, through crystalline order. And that floating has insulated freshwater bodies through ice ages, maintained the thermal refuges that aquatic life needed to persist, moderated planetary climate through the anomalous heat capacity of the oceans, and made possible the liquid water that all known biology requires. A single anomaly in the behavior of one small molecule, two hydrogens, one oxygen, 104.5 degrees, and from that geometry, life, climate, the physical history of a planet. When Dirac found deep relationships, when an observed number turned out to reflect fundamental structure all the way down, he found it beautiful. Not because beauty is separate from truth, but because the kind of coherence that runs from quantum mechanics to snowflakes to the survival of fish through winter is the kind of thing that tells you the universe has been consistent at every scale. Ice floats. You've always known it. You just didn't know how deep it went.